Welcome back to our session. We're still investigating terminal voltage, but now we'll focus our attention on a closed circuit and try to take readings across the battery and see if there are any changes and talk the science behind that. Right. So we are measuring voltage once again across the battery, but we're going to construct a same circuit. We're using a 12-volt battery, but emphasis now, we're going to close the switch and make our observation, okay? And then talk the science behind that. And then also we'll use the ammeter and voltmeter to take readings. We'll still use our 6-ohm light bulb in our circuit. So this is the setup. Now let's go straight to our simulation and see what happens. Right. So if you look at the voltage across the battery is 12 volts. Okay, this is actually our EMF reading. So this is the maximum energy of 12 volts for every coulomb of charge. Right, so the switch is open, there's zero current. You can also confirm the resistance of the light bulb is 6 ohms. Right, so what we're going to do now, we're going to close the switch and see what happens. The moment we close the switch, we realize that there's a drop in the reading of voltage across the battery, while now there's a current of 1.5 amperes. Right, now we will go back to our slide and talk the science behind that. Right, so this is basically what we obtained from that setup when we closed the switch. Right, okay, what does this mean? The voltmeter reading now, when the switch is closed, emphasis is on that, okay, that's a closed circuit. The reading has dropped from 12 to 9 volts. Now, and also the current reading, when we closed the switch, it changed from 0 to 1.5 amperes. And also, what is it that we observe? The bulb is glowing. Right. Okay. Now, what conclusions can we draw from these observations? Now, there is a terminal voltage of 9 volts across the battery while the switch is closed. Okay. Then there's a current of 1.5. The potential difference across the light bulb it's actually something also that we can measure. We can go back to our simulation and measure the potential difference across the light bulb, which is the same as across the battery. Right, okay. So we will go back to that, okay. And then we're saying the work done by the charges in the circuit in moving through the light bulb in the external circuit, there is work that is done, while when the switch was closed, work was not done. So now the difference is that work is done. Right. Okay, and then let's look at the Microview, which explains the science behind these observations. Now, the 0 joule per coulomb of charge is something that we would have obtained when the switch was open between any point except across the battery. But the potential difference across the battery, we recognize that it was 12 joules, right? Now, in this case, it becomes 9 because we've closed the switch, and then there is current in the circuit. Now the terminal potential difference is 9 volts, right? Okay, and then what exactly is happening in terms of potential difference? You realize that the potential difference across the battery is 9 volts, which comes from 12 minus 3, right? And anyway, along the conductor, there's a potential difference of 12 between any 2 points, right? Now, this suggests that the wire or the conducting wires offers 0 resistance. Similarly, the ammeter, across the ammeter, there's a potential difference of 0. So it means there is 0 resistance on the ammeter. So we can safely say or conclude or assume that the ammeter has negligible resistance. But what's the voltage terminal difference, potential difference across the light bulb? We still get the 9 volts that we managed to actually measure. Right. Now, let's compare the 2 circuits, the open one and the closed one. Now, the terminal potential difference when the switch was open was 12 volts, all right, which is the maximum. while we closed the switch, the value of the terminal potential difference dropped to 9 volts. That's very, very important. And also, the ammeter reading in this case is equals to 0 when the switch is open. When we close, now there is current in the circuit of 1.5 amperes. Right, these are just observations that we made from the setup in the simulation. Right, so in an open circuit, we've got terminal voltage of 12 volts, which you obtained, while the closed circuit is 9 volts. Now, the big question that we have to ask ourselves, what happens to the lost volts? Right, the word lost is put in those characters. Why? Because we know that voltage has to do with energy. Okay, and we know that energy cannot be created or destroyed. But then how do we account for these lost volts? Right, so where was more work done by the charges in the closed circuit? Because in the closed circuit, there was a difference, a drop in the reading by 3 volts. Right, now what are we saying? A battery has some internal resistance. So this is something. Now, there is some internal resistance in the battery. As you can see, that is inside the battery. So there is some small resistance inside the battery. Take note of the symbol of the internal resistance, small letter R. So what does that mean? It means work is done, or energy inside the battery is converted to heat as the battery does work in terms of per coulomb of charge. So when a battery is connected to a circuit, energy is dissipated because of its internal resistance. So not all the maximum energy that the battery can provide is turned into electrical energy, but some of it is converted to heat energy, right? So a relatively small amount of electrical energy is converted to heat. So this would think of it as lost because it doesn't become electrical energy. Right, so the terminal voltage in an open circuit, okay? Now the terminal voltage for an open circuit is called the EMF of the battery. This was the 12 volts in this case that we managed to record. So the EMF of the battery is the actually maximum energy stored per coulomb of charge. So the EMF of the battery does not change, it stays the same, right? But then the terminal voltage for a closed circuit, now we're looking at the closed circuit, is the potential difference of the external circuit. So that 9 volts is actually the terminal voltage of the external circuit. Okay, so stored energy from the battery is converted into heat inside the battery and light when the charges are actually moving through the resistors or the light bulbs of the circuit. Okay, so the 3 volts is inside the battery, then the 9 is actually outside the circuit, which has to do with the resistance of the light bulb. So V external or external voltage is the potential difference of the external circuit. So the external circuit, we're talking about your conducting wires as well as the light bulb. Right, okay, so lost volts, okay, and remember this is lost in the sense that it's not converted to electrical energy. So the difference between EMF and V external is actually the lost volts. So inside the battery there is an internal resistance of R, which can change depending on the type of source that is used. So stored electrical energy is converted to heat when charges move through the battery. So what about internal voltage? This is the potential difference of the internal circuit due to the internal resistance of the battery. Right. Okay, so when we talk about the battery and the resistors in this in the external circuit, we know that the internal resistance of the battery and that of the light bulb is actually in series. So whatever current passes through the battery will pass through the light bulb in this case. So resistors in series are potential dividers. Now this takes us back to some of the stuff that we know. When we have got 2 resistors that are connected in series, we know that potential difference is divided, okay? But then the amount of current that passes through the battery with its internal resistance will be the same as the current that goes through the light bulb in this case, because the internal resistance of the battery as well as that of the light bulb are actually connected in series. So they receive the same amount of current, okay? Right, so in other words, we are saying that this maximum potential difference, which is the EMF, is split between the external circuit and the internal circuit, which is the battery in this case. Right, So in short, we are simply saying that EMF becomes the maximum, okay, voltage. But this maximum voltage is actually for the battery, right? Okay. So in other words, we had 12 volts of EMF of 12 volts, right? And then we found out that the voltage that goes externally to the light bulb, we measured it across the light bulb, which we can even go on to confirm it. It's 9 volts, as you can see from the simulation, right? Okay. Now, so the external is 9 volts. So how much was lost, or the drop? The drop was due to the internal resistance. So the voltage due to the internal resistance of the battery is 3 volts. So in other words, we can simply say 12 volts is equals to 9 volts plus 3 volts. Okay, so that becomes our E. That's our V external. Okay, and then obviously that's our V internal. Okay, so these are actually our potential dividers, as we would like to refer to it. Right.